I am Francois Bouttier. I'm a scientist working in Météo France, and I will discuss ensemble nowcasting of thunderstorms and flooding. So by seamlessness, we mean that we would like to extract information from a complex set of numerical predictions. So that's important for thunderstorms and flood hazards, because these phenomena have short time scales and they may sometimes have very low predictability. That means they require very fresh forecasts, so frequently updated forecasts to issue the appropriate warnings. So there is a variety of prediction tools available. Actually, there are many of them, and for many users, there's too much information to take in. For instance, there are the observations, which can be used for nowcasting, either as persistence. Sometimes they can be extrapolated over short timescales. Then there are numerical nowcasting models, which are NWP models, so weather prediction models that are configured with very short cutoffs and rapid update cycles. So these can be combined with conventional numerical weather prediction and longer range forecasts. So usually the forecasts from NWP with longer cutoffs will have better quality, but they will be less timely, so they may or may not be useful for nowcasting. So to cope with this mass of information in real time, it is suggested here to treat all of them as a large ensemble, where the members, they are heterogeneous, they do not have the same quality, and then the ensemble size depends on the forecast horizon, as we will see in a minute. And then this ensemble has to be interpreted as probabilistic information and translated into terms and products that are simple enough for the users, in particular to hide the discontinuities and artifacts related to the heterogeneity between the models and biases and calibration issues. So we will discuss three kinds of themes, so to speak. So there are the discontinuities between the prediction models that we would like to blend. Then there's the gap between what's modeled in the ensemble prediction systems and the parameters for which you would like to issue probabilities. And then there's the translation of numerical weather prediction information into understandable user warnings. So regarding the time continuity of the forecast products, it is useful to visualize the diversity of forecast models in a typical production suite as a two-dimensional diagram, where in the horizontal you have the validity time of the weather products, and in the vertical you have the production time, so the time at which the models are computed. So the diagonal, the gray diagonal is the present, and to the right you have the future. So the navy arrows, short arrows, represent the nowcasting systems, which are frequently repeated and have very short forecast horizons. And then from time to time, there will be a longer range forecasts, either deterministic or ensemble predictions, who will tend to start later in the past because they require longer time to prepare the initial condition and perform the computation, but they will reach further into the future. So when elaborating an end user forecast, we would like to combine all this information in a data window represented here in the dash gray. And in that window, we treat all the up-to-date forecasts as an ensemble. So some arrows are shorter than the others. That means that short time ranges, you will have more members than at longer time ranges. And that window is moving as time goes by. So that it's important to minimize the jumpiness in the forecast. So as new forecasts are introduced in the update of the forecasting products, we want to avoid discontinuities, and we want to avoid jumpy warnings. That is, we don't want to issue a warning that we'll have to cancel and reissue a few hours later. That's very inconvenient for many users. Another requirement of time continuity is that the forecast products should relax to the observations as the forecast horizon tends to 0. So then there's the discontinuity in parameter space between what is available in the models, including the nowcasting systems, and the parameters in terms of which we need to make warnings. Taking as an example the thunderstorms, where there are many possible impacts that are possible from a thunderstorm cloud. Some are easy to observe and are relatively well modeled nowadays, like radar effectivities or satellite cloud tops. Others, like tornadoes or hail, are much more difficult to observe and to model. So the quality of the forecast will be a function of the quality of the clouds that are in the forecast models, but also our ability to diagnose user-oriented parameters from these model states. And that's an area of active research. Then there's an important issue for thunderstorms and heavy precipitation, that these parameters, these events tend to be relatively small and short-lived, and their forecast errors are of the same order of magnitude as the event itself. And that means that there will be what we call the double penalty. That is, that if you make a straight forecast product from interpretation of the forecast on the model grid, if the model has a high resolution, so if it simulates high resolution events, most of the forecasts will be wrong, as explained on the slide, because with even small displacement in place or time of the forecast events, you will have a majority of wrong forecasts, either false alarms or missed events. And that is very bad for the user experience. So the solution to this double penalty problem is to express the forecast in probabilistic terms. That means that instead of forecasting, in the example, a storm risk on point X only, you will forecast it with a limited trust on a wider area. That will increase the detection rate. And obviously, there's a compromise to be found between the detection rate and the number of false alarms, so that it has to be decided with respect to the kind of users and what the users require in terms of the number of false alarms. So to issue probability forecasts, the tool of choice is the Ensemble prediction. So as you know, Ensemble prediction is the process of running in parallel several numerical forecasts that are perturbed in such a way that they represent a sample of the possible future evolution of the atmosphere. And they can be used to quantify the probability of high impact weather events. So here is an example with a 12-member rain forecast, where there are a few members correctly predicted a high precipitation event. So if you have time, you can may look at each of the 12 members on the left, but we would like to summarize this information. So one way to summarize would be to convert at each point the forecast field of precipitation using, say, a quantile statistic. So if I extract the 85% percentile shown at the top right, we get a smooth field. But the big problem is that the maximum precipitation is removed, even with such a high percentile, because the event, the high impact event in this case, is intense, but it has a small scale and there are uncertainties on its location. So to avoid this damping of the signal, it's necessary to do more clever processing of the ensemble output, typically neighborhood methods. And here it's an example on the bottom right, where we have applied a max neighborhood of our small radius, plus statistical calibration to remove ensemble biases. And that provides a summary of the ensemble prediction with the more or less correct amplitude and location of the hazardous area. So speaking of flood, so that there's a complicated relationship between precipitation forecast and flash floods. So precipitation is the main cause of flooding, but it has to be processed with care, because instant precipitation rain rates are a poor predictor of flood risk. If you may have seen weather events where there's intense rain, but from moving clouds, so that there's no accumulation that's hazardous anywhere. On the other hand, you may have moderate precipitation with coming from clouds that move, but they tend to repeat themselves over the same places because of what we call convective regeneration, which is often linked to orography or convergence lines. So it's important to assess the flood risk in terms of rain accumulation using a model that's as physically realistic as possible, so that it should represent these processes. So speaking of AI, that means, I mean, these events are fairly intense and high impact, but they have a complex structure in space and time, and it's difficult to guess from examination of the rain field in real time whether we are having catastrophic accumulation or not. So conventional OPS extrapolation methods are difficult to use for this kind of systems, because there's a complex relationship between the motion, the rain field, and the flood risk. So there are other problems linked to the hydrological aspect of the flood formation. In particular, the vulnerability of the populations to the flood is very dependent on the local history of extreme precipitation and floods. And so when issued the warning, it's important to pay attention to the climate of precipitation accumulation in a very detailed way, to assess whether this is a normal event or whether this is an extreme that is hazardous. So in summary, these complexities mean that it's important to process precipitation forecasts not as a scalar field, like we have done for thunderstorms, but we need to pay attention to the space and time structure of the precipitation scenarios, and extract the quantities that are really important for flood prediction. So here's an example of that. Precipitation forecast errors are usually heavily correlated in space and time. So, for instance, if you take 2 quantiles of rain accumulated over 3 hours, so shown on the left, 2 plots, and you sum them, you will get a field that's very different from the 3-hour accumulation of rain. In other terms, the sum of rain quantiles is quite different from the quantile of the rain accumulation. So you cannot just issue short accumulations of rain, derive probabilities from that, and derive flood forecast from that, because the flood is sensitive to accumulation over several time scales. And if you neglect that, you will usually end up with very large errors in the prediction of rain accumulations. In this example, we have up to 30% error in the prediction of the high precipitation area. So we will finish by 2 examples of pre-operational products that use these ideas. So one about Thunderstorm. So this is a forecast product, the short-range forecast product of Thunderstorms that is a blend between 3 Ensemble prediction systems that are very different from each other in terms of forecast ranges, physics, and resolutions. And an evaluation of this blend shows that it's much better than each of these systems taken in isolation, even after calibration. And so by blending, we mean that we have weighted each ensemble as a function of their average quality, and the ensemble members, they are smoothed in space using a max neighborhood method, which has been tuned using a machine learning algorithm over a rather short training period to have the requested ratio between false alarms and non-detections. And that's important because it is related to the way users will perceive this product for their everyday activity. So it's a product for the wide public. As a byproduct from the machine learning, we can assess the effective predictability scale of thunderstorms, which in this case is of the order of 70 kilometers. So that's much lower than the resolution of the AROM system, which is the highest resolution model, which has a kilometric scale resolution. So that shows the predictability of the thunderstorms in current systems. And an example about prediction. So this is a nowcasting system that uses deterministically a blend between an optical flow extrapolation of sequences of radar images and short numerical forecasts from a kilometric scale model. So every 15 minutes we update this OPS model blend. So that's a deterministic rain prediction system. And we have demonstrated that the forecast quality is much improved when we use it in a probabilistic way. So we convert this deterministic system by building a per person lagged ensemble. So we use the 3 most recent members at any given time, and we apply a neighborhood processing to smooth out the small unpredictable details and optimize the forecast error statistics, so which are illustrated in the lower left diagram. So it's called a rock diagram, and it shows that we improve a lot the detection rates without creating too many false alarms by applying this neighborhood processing. So there are several ways of doing this kind of processing. One can process the rain field on short intervals as a scalar field, or we can use the scenario approach I outlined earlier by adding noise that's coherent in space and time to increase the ensemble size, because remember, it's very small, and compute probabilities after that operation. So each of these two methods have their own benefits, and we are still working to determine what's the best solution. So as a conclusion, how can we improve the nowcasting of thunderstorms and flood along these lines? So there are two avenues. One is to improve the forecasting systems themselves. So there are ways to improve the observations and the models. Observations that are critical in many cases are low tropospheric observations, and the technologies exist, but the space-time coverage is essential for nowcasting. And regarding the models, so there are improvements that can be done in the model themselves and data assimilation, and there is potential from the artificial intelligence community, which should be combined with the numerical approaches. And on the other hand, there are ways to improve the use of the data that's already produced. So I've already described the ensemble processing methods that for which there is much to be improved. And it's important to realize that the probabilistic processing of forecast output, it's sensitive to the users for which the products are meant. So that means more work to optimize the product for each of them. And I recommend using as much as possible several model systems because it's a consistent result that forecast products can be much improved thanks to the combination of independent prediction systems. And lastly, I often get the question, why don't you use AI methods for nowcasting? Well, there's a basic problem that these high impact thunderstorms and flooding in particular, they're still relatively rare events compared to their complexity. So it's still difficult to build the training samples to use sophisticated AI methods, but we will see in the future what they can do. That's the end of my talk.
All right.
Thank you. Have you got any question?
We're a little bit tight for time, but I think you had some questions on the chat, so you might want to respond to them afterwards. But there was one question that, and I think you addressed several of them, but the one question was, how do you foresee, this is from Beth Ebert, how do you foresee blending observational-based nowcasting systems that are probabilistic? And I think she's thinking about the steps algorithm for precipitation, and how do you combine it with the model ensembles? So how do you combine observational-based ensembles and model ensembles? How do you envision that?
Well, the proposal is to treat them as an ensemble, as I described in my talk. So the observation-based extrapolation can be regarded as one ensemble member, which is very short. And when you derive probability, you can combine the information from that system with the numerical prediction system. So you don't need to do interpolation of the fields themselves, but you use several members in your probability computation.
Right. So take a look at the question from Beth. It's because she sees it as different fields. Anyway.